The first speaker today is Pierre Yves Gaudreau Lamarre from Syracuse University. He will speak us about critical signal detection and reflected Brownian motions. Enjoy the talk.
All right. Thank you for the introduction. So before I begin, I'd like to first thank all the organizers of this event for the very kind invitation to come and give this talk. It's my great pleasure to be here. And also, I want to mention that later on in this talk, I'll discuss various joint works with Promid Gassal, who's an assistant professor at Brandeis.
When did she go there?
Sorry?
When did Promid go to Brandeis?
Last year.
Last year.
Right. Wilson Lee, who's a very talented graduate student at Harvard. Yuchen Liao, who's a postdoc instructor at Wisconsin-Madison, as well as Mikhailo Shkolnikov, who recently moved to Carnegie Mellon, who used to be my PhD advisor from 2015 to 2020. And what I want to talk about today is a number of recent works that are all stemming from a remarkable connection between a certain class of random matrix problems having to do with signal detection problems and reflected Brownian motions that has been gradually developing in the literature in the past 20 years or so. And my plan for this is the following. So first, to motivate my work, I'm going to begin by going over one simple instance of the kinds of signal detection problems that I'm interested in. And I'll finish this first section by stating, a theorem that I claim I can prove regarding these signal detection problems. Following up on this, I'll connect back to the subject of this workshop by explaining what is the connection between the signal detection problems and theorems we saw in section 1 and reflected Brownian motion. And then at the very end, I'll explain how this connection can be exploited to prove the result I have in mind. So with this said, let us begin with the motivation. So here's a basic setup for one of the kinds of signal detection problems that I'm interested in. Suppose we're given a positive integer capital N that is very large. Eventually, this is a parameter that we're going to send to infinity. But before doing this, given a fixed finite n, we're going to let capital G be an n by n symmetric random matrix that is sampled according to the so-called Gaussian orthogonal ensemble, or GOE, which is just a fancy name for the standard Gaussian distribution on the space of symmetric matrices. And this is something that we can justify by looking at the density function of this matrix ensemble, which is given by 1 over some normalization constant that ensures that this density integrates to 1, times the familiar Gaussian exponential of minus a constant times the squared norm. And the norm that we use on the space of matrices is the Frobenius norm. Okay? And the reason why we're looking at these particular random matrices is that we want to think of this G as a sort of purely white or unstructured noise inside of which we're going to embed a hidden signal that we're going to try to detect. And it turns out that there are various properties of these GOE matrices that make them a very natural model for a white noise in the space of matrices. Among other things, as I've said, we can... In what context?
Is this modelization appropriate?
Well, so we're going to get to this. So there is one property of this GOE that makes it a very compelling model for white noise. And the first thing we can note about this is that this is a sort of standard Gaussian in the sense that the expectation of every entry of GOE matrices is 0, and the typical size of a GOE matrix as measured by its operator norm is of order 1 as you send n to infinity. And the most important property from the context of viewing this as a white noise is that in direct analogy to standard Gaussian vectors in Rn, the GOE is isotropic in the sense that if I give you some fixed orthogonal matrix O, and then we do a change of basis by conjugating the matrix G by this O, then what we obtain as a result of this is still in distribution a GOE. Okay, so GOE matrices in some sense do not have any preferred direction in space, and thus we can view them as a purely unstructured noise in the space of symmetric matrices. So we view this as the background noise, and then as I said, we want to hide inside of this a signal. So the signal itself is also a matrix. I'm going to call this capital L. This is a deterministic n by n symmetric matrix. And one crucial assumption that we make about this signal is that we want the rank of this matrix, which I denote by lowercase s throughout the talk, to be fixed and independent of the dimension n. Okay? And this is just because we view the rank of this matrix as the number of signals that we're trying to detect, and we just so happen to be interested in the problem where the number of signals remains fixed as we send the dimension to infinity. And then the only piece of information that we can use to sort of, one more thing I should say is, the actual signals that we're going to try to detect are the non-zero eigenvalues that correspond to the rank of this matrix. I'm going to denote these by lambda 1L to lambda SL in decreasing order. And I'm going to assume that they're all positive. And then, as I was saying, right, the information that we can use to try to detect the signal is what I'll call the sample matrix, X, which is just the sum of the noise plus the signal. Okay? And much more specifically than this, we're going to be interested in a very narrow problem related to detecting the signal from the sample. So if I now condense these three definitions as follows, Sorry?
Yeah, the same question. Can you give us an example of context?
Like a practical application?
Yeah.
Oh, that is a very good question. So I think we can view this as a sort of toy model. So a model that would have perhaps more immediate applications would be a sample covariance matrix with some spikes, some non-zero, some covariance structure that is non-trivial. So let's say you have an identity matrix, and then certain entries are strictly greater than 1.
In that case, the noise is not independent across elements.
The noise is not it. Well, you have a sort of isotropic background noise coming from, let's say, an identity covariance, and then you add to this, to the identity covariance, some spikes.
Statistical estimation error.
Right.
Ij and Ik is not.
Right. But this is a different type of model that is a sort of toy model that behaves in a similar way as these. So everything that I'm going to talk about today does apply to also the Wishart with spikes, but this is somehow a simpler setup for the kinds of signal detection problems that what I'm talking about applies to. All right, so the problem we're going to be interested in is to try to recover any parameter of interest regarding the signal matrix, either the rank or the signals themselves. And the only information that we're going to try to use to achieve this is the asymptotic behavior as the dimension goes to infinity of the eigenvalues of the sample matrix, which I'm denoting lambda 1x to lambda nx. So the standard approach that is used to achieve this, which is very obvious if one thinks about it for a few moments, is a two-step strategy where the first thing that we do to establish a sort of benchmark or null hypothesis is to study the asymptotics of these eigenvalues when there is no signal present, just a pure noise GOE matrix, and then compare against this the actual asymptotics that we get in our sample. And then if there's a difference between the two, this is an obvious sign that there is a signal in our sample. And so the first thing that we should do is understand what the asymptotics of the eigenvalues of a pure noise GOE matrix looks like. And this is a problem that has been extremely well studied in the mathematical literature since the 1950s, and there are lots of results about this. But for the specific purposes of this talk, we're going to look at 3 results, which I've cited here. So first, we have a result by Furedi and Kamlush, which says that if we look at the smallest eigenvalue, lambda ng, and the largest eigenvalue, lambda 1g, of this pure noise matrix, these converge almost surely to -2 and 2, respectively, meaning that in the large dimensional limit, all the eigenvalues of a pure noise matrix are neatly contained in this compact interval. And then if we want to understand what happens in between these two extremes, we have a famous result by Eugene Wigner, which states essentially, informally, that if we look at a histogram of the eigenvalues of a GOE matrix, this converges to a semicircle distribution. If this is something you've never seen before, right, here's an illustration of this result, where in blue here we have a histogram of the eigenvalues of one realization of a GOE matrix that is 2000 by 2000. And then on top of this, in red, we have the plot of the semicircle distribution from -2 to 2, which is just the plot of a half circle from -2 to 2 that is normalized to have an area of 1. And Wigner somehow formalized the notion that this histogram does converge to this semicircle distribution with a rigorous statement. And then if we want to refine this sort of result, we can look at the fluctuations of individual eigenvalues of GOE matrices. And one particular result in this direction is by Tracy and Whittam. And what they do is they look at the largest eigenvalues of this GOE matrix, these lambda k, subtract 2 from that, which is the rightmost edge of this semicircle distribution, where the largest eigenvalues of the GOE matrix accumulates, and then magnify this difference by n to the 2/3. And it turns out that this is the right amount by which you have to magnify in order to observe non-trivial fluctuations of these eigenvalues, in the sense that these rescaled eigenvalues converge in joint distribution to the points inside of a non-trivial point process, which I call E0, that has a largest point E10 and then extends to minus infinity with an infinite number of points, whose joint distributions describe the fluctuations of the largest eigenvalues in your GOE matrix. And here I should mention that the result by Tracy and Widom was much stronger than what I'm writing here, in the sense that Tracy and Widom did actually, in fact, characterize the joint distributions of the points in E0. I'm not going to go over this characterization now for 2 reasons. The first is that it's a bit complicated and would require some time to set up. And in any case, we will look at another characterization of the points in this point process later on in the talk that is completely different from the one that Tracy and Widom came up with. But I nevertheless wanted to point out that they did, in fact, characterize the distribution of these points. Okay. All right, so this gives us a small sample of some of the properties of the behavior of the eigenvalues of pure noise matrices. So now, following up on this, we can ask what happens to any or all of these asymptotics when we add a signal to the matrix, and we're now looking at the sample matrix X. And as it turns out, the short answer to this problem is that there's a phase transition in the asymptotics of these sample matrices, depending on the size of the eigenvalues of the signal matrix, that somehow differentiates between signals that are too small to detect consistently as n goes to infinity and signals that are large enough. And the general theory of these kinds of phase transition type behaviors in signal detection problems was pioneered by a series of results, most notably this paper by Baik, Benahou, and Péché, although these works here were in the context of a slightly different problem involving covariance matrices. But in the specific context of the simple problem that we're looking at here, it turns out that the phase transition that differentiates signals that are too small to be easily detected and signals that are large enough is at 1, meaning that if you have signals that are smaller than 1, you can't reliably detect them. If you have signals that are bigger than 1, supercritical, these can be easily detected. And then you have a class of critical signals exactly at the threshold where the detectability question is not quite so clear-cut. And it turns out to be these critical signals that I'm interested in. But before getting into this, let's look at the other 2 regimes. So if we think about the supercritical signals, in the case of the specific model that we're looking at here, this is something that was settled in a paper by Capitaine, Donati-Martin, and Ferral, based on some pioneering work of Péché. And what they proved is the following. So if I let R denote the number of eigenvalues in my signal matrix that are strictly greater than 1, then if we look at the almost sure asymptotics of the largest eigenvalues of the sample matrix, the R largest eigenvalues of X converge to numbers that are strictly greater than what you would otherwise get in a pure noise matrix, right? Because lambda k plus 1 over lambda k is strictly greater than 2 if lambda k is greater than 1. And among other things, what this means is that we can reliably detect the presence of any signal that is strictly greater than 1 in these asymptotics. For this, all you have to do is look at the asymptotics of the eigenvalues of your sample matrix, and then count how many outliers in these eigenvalues are sticking out of the support of the semicircle distribution, are greater than 2. So this gives you the number R, so how many signal eigenvalues are strictly greater than 1. And then, because the function x plus 1 over x is invertible when x is greater than 1, you can also recover the exact value of these signals. So for example, in this picture, by observing that we have a signal at 3 plus 1/3, or an outlier rather, at 3 plus 1/3, and another one at 2 plus 1/2, we can work out from this that our actual signals must be 2 and 3, okay? And so this illustrates somehow that supercritical signals can be detected consistently in a straightforward manner. In sharp contrast to that, we have that subcritical signals smaller than 1 cannot easily be detected. So this is based on a series of works by Blumendahl, Virag, and Zhang, Chang, and Li, based on some pioneering work by Montanari, Reichmann, Zeytouni, and Péchet. And among other things, what can be proved in this scenario is this. So suppose now, for instance, that all of our signal eigenvalues are strictly smaller than 1. In this case, it can be proved that any almost sure asymptotics of any number of the eigenvalues, either from the pure noise or sample matrix, are always the same. And in particular, at very best, right, if you try to develop any kind of statistical test that distinguishes between competing hypotheses, where we try to count how many of these subcritical signals that we have, right, the best performance or asymptotic power that any statistical test will have will always be strictly smaller than 1 in the limit, in the sense that the probability that you correctly reject one hypothesis if a competing one is true will always be strictly smaller than 1. So it's impossible to consistently detect the signals in this case. And even if we look at the fluctuations of the largest eigenvalues, well, these fluctuations are exactly the same as the pure noise case. So you can't detect the presence of signals even by looking at the fluctuations of the largest eigenvalues. And so now this leaves out the sort of in-between case of critical signals. So this is something that has been studied in depth in a paper by Blumendahl and Virag. And among other things, what they proved is this. So suppose now, just for simplicity, that we are in the case where the largest eigenvalues in our signal matrix are exactly equal to 1. Let's say that we have R of these signals equal to 1, and all of the other signals are strictly smaller than 1. So thanks to the result by Capitaine, Donati-Martin, and Ferral that we cited earlier, the almost sure asymptotics of the largest eigenvalues in this case are equal to 2, which is the same as what they would be in the pure noise case. However, the fluctuations now are different in the sense that Blumendahl and Virag showed the existence of a family of distinct point processes that are indexed by this parameter R that counts how many signals are exactly equal to 1, which describe the limiting joint fluctuations of the largest eigenvalues in the sample matrix. And here we have exactly the same scaling as in the case of the pure noise matrix. It's just the distribution in the limit that is different. Okay? And so here we will describe the joint distribution of these points in just a moment. But before we get to this, just to conclude this first section, right, the fact that we get different distributions here hints at the possibility, perhaps, of being able to recover the number of critical signals that we have in this situation. However, recovering the parameter R from this sort of limit is much less straightforward, of course, as in the supercritical case. Because in the supercritical case, we had some deterministic almost sure limits. So just a single observation of these numbers tells you how many supercritical signals you have, as well as their magnitude. Whereas here, right, if we want to recover the number R, we're trying to recover the parameter R from a random infinite set of points. And in principle, one single observation of this point process might not be enough to recover the parameter R. Yes?
But in fact, this is because you assume you know the normalization of the noise.
Right.
One is in fact the variance of the noise.
Right, correct.
Actually observe the sum. That's very tricky. But use this in practice, and the main thing is where to put the threshold.
It's true, yeah. In this, we assume that sigma is known, basically, which the variance of the noise, right? So, right. So this is I guess purely in theory, it is straightforward, correct? If you do know the variance of the noise.
You cannot assume it's not one, it's something.
Right.
Then you can, so you need to estimate the threshold. So
I see.
And you would want to use this result, so you estimate the threshold as to maximize or as to minimize the distance between the truncated distribution on the left and the narrow.
Right.
But that's the crucial.
I see.
Otherwise, if it's close to one, it's
Right. So in this sense, right, the problem that we're contemplating here, let's say purely in theory, is what do we need to recover the parameter R in this case from observations of this point process. And the claim that I'm making is that, in fact, we need one single observation in principle of this point process, in the sense that these point processes are mutually singular in the space of point processes. And more specifically, what I claim is that there exists a fairly explicit deterministic function f, such that for any number r greater or equal to 0, if you evaluate this f into one single realization of this point process, it gives you out the parameter r. Okay, so you just need one realization of the point process to recover the parameter. All right, so this is all I wanted to say about the sort of signal detection motivation for this problem, as well as the theorem that I'm claiming we can prove here. So now, before we move on to going through the connection between this kind of thing and a reflected Brownian motion, are there any further questions about the basic problem that we're looking at, as well as the claim we're making here? Yes. Well, so it depends on the normalization. So because the GOE has several definitions, and I'm using the definition with this over here. So there's already the square root n built in. But you're right that if you use the GOE where the variance of individual entries is of order 1, then you do need to add this square root n. That's right. Right, right.
So in this normalization, the error on the threshold is 1 over square root of n.
Right.
And the width of the trace equivalent is smaller. It's 1 over 10 to the third.
Right. Right.
You can't see it finite.
Right. Right. So this is purely an asymptotic result. And the question is, what kind of information? So basically the theoretical question I'm asking here is, what information about R is contained in this limiting point process? And it turns out that all the information is contained about R. So there is a legitimate question to be asked about how we can actually use this in inference theory, finite n, and this is completely open. Yes.
In the case of GO, it's like you are somewhat E0 is the counter for a process.
Mm-hmm.
That property remains.
Yes. In fact, you can also, so I guess you're thinking about general beta. You can also detect beta almost surely from one single observation of the stochastic area spectrum. Okay, so let us then explain how we can prove this result. And the first thing I should do here is, explain what is, how we can characterize the joint distribution of the points in these point processes ER. So to do this, we need to take a slight detour into the fascinating theory of operator limits of random matrices, which was pioneered in a paper by Edelman and Sutton, which itself was largely inspired by prior work by Dimitriou and Edelman. And what they did in this paper, essentially, is they looked at a number of very classical random matrix models that had been studied for decades, and noticed that if you look at rescalings of these random matrices that sort of zoom in to the fluctuations of the largest eigenvalues, and apply a series of very clever rotations to these matrices, you can just about make out that the rescale matrices converge to some infinite dimensional random operators whose eigenvalues give you the point processes that describe the fluctuations of largest eigenvalues. And in particular, they derived some very precise blueprints for what these operators should look like. And so what emerged from this paper was a very active program to try to rigorously prove all of these predictions. So in the case of GOE matrices, this was done in a landmark paper by Ramirez, Ryder, and Virag, among many other things, and then later extended to the case of sample matrices with critical signals in 2 follow-up articles by Blumenthal and Virag. And here, skipping over how this literature actually works and just showing you the end result of it, here is what we get. So first, if we consider the case of R0, which means that either we have no signal or just a subcritical signal, so suppose that W is a Brownian motion, and that we define the so-called stochastic area operator, S0, as an infinite dimensional operator that acts on a vector subspace of squared integrable functions on the positive half line from 0 to infinity, which satisfy a Dirichlet boundary condition. And the action of this S0 on such a function is given by the second derivative minus the pointwise product of the linear function f, x with f, plus 2 times the pointwise product of the derivative of a Brownian motion with f, then it can be proved that if we look at the rescaled version of the sample matrix that sort of zooms into the fluctuations of largest eigenvalues, this converges to S0 in the sense that the point process, E0, that describes the fluctuations of these eigenvalues, is given by the eigenvalue point process of this random operator. Okay? And here, one thing I should mention before moving on is that, of course, there's one aspect of the definition of this object that is a bit ambiguous, which is that, of course, sample paths of Brownian motions are not differentiable. So what exactly do I mean when I say that the action of this operator on the function f involves the pointwise product of the derivative of w against the function f? So there are some technicalities involved in making sure that this object can be defined rigorously, which in part explains why there was a gap between the realization that this operator is the limit of these sample matrices and the actual proof. And conceptually, to make this work, the idea is relatively simple, right? You just settle on a weak definition of this spectrum in the sense that when we say that a number lambda and a function f form an eigenvalue-eigenfunction pair for this operator, which formally means that S0 of f equals lambda f, what we actually mean by this is that if you look at the integral of S0f against any test function g, this is equal to the integral of lambda f against g. And now if we expand this S0f according to the definition of the stochastic area operator I gave you in the previous slide, right, we can isolate this problematic term with w prime just as a stochastic integral of these functions to fg with respect to w, which is not problematic. And there are some very difficult technicalities that are involved with making sure that the weak definition of the spectrum in this way actually coincides with the fluctuations of the largest eigenvalues of these GOE matrices. But conceptually, this is how you can make sense rigorously of these operators and their spectrum. And then following up on this, there were some extensions to the fluctuations of signal matrices with some critical signals. So in the case when we have one critical signal, lambda 1 is equal to 1, and then all the other eigenvalues are smaller, in this case, the limiting fluctuations, E1, are described by the eigenvalues of a slightly different stochastic area operator that I'm going to call S1. The action of this operator on a function from 0 to infinity is exactly the same as S0. The only difference is that now we assume a Neumann boundary condition in the domain instead of Dirichlet. So this changes the eigenvalues slightly. And then following up on this, the general case of any number of critical signals was settled in a second paper by Blumendahl and Virag. And here we have a slightly more complicated operator that characterizes these fluctuations. So suppose now that WR is a symmetric matrix-valued Brownian motion, right? So this is just a function that takes values in the space of continuous functions with symmetric R by R matrix-valued outputs. And the increments of this are independent and given by properly rescaled versions of GOE matrices. And now we define the multivariate stochastic area operator, SR, which acts on vector-valued functions with R components. Each of these components is an L2 function from 0 to infinity, and every component here satisfies one of these Neumann boundary conditions. And the action of SR on a function f like this is just the second derivative on each component individually, the pointwise product of minus Rx also on each component, and then the matrix product of 2 times the derivative of this matrix Brownian motion onto this vector-valued function. And this is also something that we can define rigorously using quadratic forms with a bit more difficulty. But the fact is that the limiting fluctuations of the largest eigenvalues of sample matrices in the case of R critical signals are given by the eigenvalues of this random operator. Okay? Positivity? No.
Test functions are
Test functions. I mean, so the 0 infinity here comes from the fact that when we're setting up the limiting argument to associate finite dimensional random matrices to this, we start with a 0 entry at the origin, And then the entries from like 1 to n correspond to grid points that approximate, the 0 infinity interval. So basically, we're viewing space, the space on which matrices act of components from 1 to n as a sort of grid that approximates 0 to infinity. So, in addition to providing a characterization of these point processes, this allows us to, come up with a purely functional analytic reformulation of the theorem that I claimed earlier, which is that there exists an explicit deterministic function f such that when you evaluate this in the eigenvalues of one of these stochastic area operators, you can recover the parameter r from this almost surely. So in other words, if I give you one realization of the eigenvalues of these operators, and the only thing I tell you is that this is coming from one of the stochastic area operators, you can recover from this, information about the domain on which the operator acts, namely, if this is one of these vector-valued stochastic area operators, or one of the scalar-valued ones. And in the scalar-valued case, you can distinguish between either this Neumann boundary condition for S1 or this Dirichlet boundary condition for S0. Okay. So with this said, we are now finally in a position to appreciate where the connection between this sort of problem and reflected Brownian motion comes in. And it comes from the Feynman-Katz formula. And more specifically, the fact that the approach that we've been using to sort of solve this kind of problem is to study the exponential trace of these stochastic area operators, right? The trace of e to the t of these SR operators, which is nothing more than the sum of these exponentials e to the t of the eigenvalues of these stochastic area operators as t goes to 0. And there are two main reasons why this is an attractive strategy. The first reason comes from very general considerations in analysis, more specifically the field of spectral geometry or exponential trace asymptotics. And as it turns out, right, for very, very general classes of differential operators, if you look at the asymptotics of the exponential trace as t goes to 0, you can usually expand this, as a power series in terms of t, where the coefficients in the power series, these alpha 1, alpha 2, alpha 3, and so forth, contain a lot of very precise information about the domain on which the operator is defined. Okay, so that's just a general fact from analysis. Yeah. And so what we're hoping here is that in the case of these stochastic area operators, if we're able to carry out power series expansion of this type, then the coefficients, which some of which presumably will depend on r, will allow us to recover almost surely the parameter r. Okay? And then the second thing is based on the particularities of the specific operator we're looking at, which is that we're not just looking at any kind of differential operator, but in fact a diffusion operator. And so we can apply the Feynman-Katz formula to calculate these exponential traces. Just to give you a simple example, right? If we look at an operator that is similar to S1, right, which is a sort of diffusion operator that involves the Laplacian plus a pointwise product with a function v, acting on a domain of functions on the positive half line subject to this Neumann boundary condition, then the Feynman-Katz formula tells us, among other things, that if we look at the exponential trace of this operator over 2, we have a completely explicit probabilistic representation for this, which involves, the simplest instance possible of a reflected Brownian motion, just basically the absolute value of a Brownian motion that is one-dimensional Brownian motion that is restricted to stay on 0 infinity. In this expectation, zxxt, this is just the reflected Brownian bridge that is conditioned to start and end at x in between times 0 and t. And what we're doing here is we're integrating over this parameter x the expectation of the exponential of the integral of the path of these reflected Brownian bridges with respect to their starting points, evaluated in whatever is the function v that we have here. And then we also have this other term, pt, which is just the transition semigroup of the reflected Brownian motion. And so what this hints at least in this special case, is that these exponential traces, whose asymptotics we expect contain a lot of useful information about the parameter that we want to recover, are amenable to computation using stochastic analysis. Right? However, we have to be a bit careful before we get ahead of ourselves in this program, and remember that the operators we're dealing with are quite singular. right? Because the v that we have here is not just any function, but in fact involves these derivatives of Brownian motions. And if we just naively try to write down the Feynman-Katz formula, we run into some problems. So for example, if we try to use the formula I gave you in the previous slide to write the exponential trace of S1, then we have this term, right? The integral of the path of these reflected Brownian bridges evaluated in W prime, which doesn't quite make sense. And so as it turns out, it is possible to get around this difficulty. And the theory of the Feynman-Katz formula or semigroups for these kinds of operators was pioneered in a paper by Vadim Gorin and my used to be PhD advisor, Mikhailo Shkolnikov. So in this paper, they settled the case of S0, the operator that describes the fluctuations of a subcritical signal matrix. And then the first problem that my advisor gave me when I was a PhD student in 2015 was to try to extend this result to the case of SR, R greater than 1. Back then, we were only able to settle the case of S1 of the stochastic area operator with one critical signal, because it turns out that the Feynman-Katz formula for Schrödinger operators or diffusion operators with acting on vector-valued functions is a lot more difficult to deal with than the scalar case. So since 2015, this is a problem that I had been interested in, tried to solve many times, and that I finally this year was able to make some progress on. And in the case of SR, R greater than 1, what we have are formulas for the moments of these exponential traces. But just to give you a small idea of how this works, at least for S0 and S1, conceptually, the basic idea to make sense of this is relatively simple. So, and it's a very classical idea in the field of SPDs. So basically what you do is you exploit the fact that if you're looking at the integral of a measurable function f evaluated in the path of a reflected Brownian motion, you can always rewrite this as the integral of f over space times the local time process of z. Right? And then if you just pretend that this formula makes sense even when f is the derivative of a Brownian motion, this gives you, a natural candidate for what this problematic term in the Feynman-Katz formula should look like, the integral of W prime against the local time, which is just the stochastic integral of local time with respect to your Brownian motion. And as it turns out, it is a theorem that for S0 and S1, understanding the problematic term in this way actually gives you a Feynman-Katz formula. Right? So we do have a Feynman-Katz formula for S1, for example, if you just replace this term by the stochastic integral that I showed you. In the case of SR, right, it's unfortunately a bit more complicated than this, and I don't have enough time to really get into the details, but I'd be more than happy to go over the details if you're interested after the talk. But the main point that I want to make from this, right, regardless of the specificities of each different case, is that what emerges from this theory is the ability to calculate the moments of these exponential traces. And these moments can be expressed in terms of fairly straightforward functionals of reflected Brownian motions. Yes? I guess technically it is because it's not allowed to touch 0. It's killed as soon as it does, but yeah, that's right. You can, right, that's right. But yeah, it's true that you can write it as just a Brownian motion that is killed at 0, and then that makes things much easier, yeah. So to give you, again, just one example, the kinds of formulas that you get from this theory look something like this. So for example, in the case of S1 again, if you look at the expected trace, you just get this simple functional that only requires understanding the joint distribution of the area under the path of a reflected Brownian motion, as well as this functional SIT here, which is the self-intersection local time of the reflected Brownian motion. Just essentially, this counts how often the path of Z intersects with itself. And then if you look at higher moments, right, the formulas become a bit more complicated. For instance, if you look at the variance, now we have a double integral, right, which involves the paths of two independent reflected Brownian motions, Z and Z tilde. And now understanding this requires understanding the joint distribution of the areas under these paths. Again, the self-intersection local times of both of them, as well as now the mutual intersection local time between these two paths, which counts essentially how often they intersect with each other. And we can imagine, judging from these basic examples, that if you increase, the power of the moments, the formulas become increasingly complicated, but they still always involve these kinds of intersection functionals of the paths. And again, if we increase R, you also get something slightly, somewhat similar, except that now the diffusion becomes more complicated. It's a sort of reflected Brownian motion that is decorated by a jump process on the vertices R, but it's still some kind of reflection, self-intersection and mutual intersection functionals that are involved in these formulas. And so then the last thing I want to talk about is, now that we are armed with these things, how can we exploit this to prove the result that I claimed? So the first step in analyzing the trace asymptotics is to control the fluctuations of these traces as t goes to 0, because of course, any contribution to this trace that is of greater order than the variance, we will be able to extract almost surely. And so this is something that was done in a series of papers. First, in the case of S0 and S1, this was done in some joint work with Pramit Gasal, Wilson Li, and Yuqin Liao, and later extended to the general case of any number of critical signals in my most recent preprint. And what we can prove here is that, on the one hand, the variance of these exponential traces remains bounded as we send t to 0. Okay? And this is optimal in the sense that if we look at the simplest cases, in the case of S0, for example, we can actually prove that the limit of the variance converges to a finite number. Okay, so these variances in general don't go to 0. So that's the optimal sort of bound that you can get for this. And moreover, these exponential traces for small time become uncorrelated in the sense that if you fix any t1, and then you look at the covariance of the exponential trace at t1 and t2, where you send t2 to 0, this vanishes. Okay? So this forms a sequence of random variables whose fluctuations are bounded and which become uncorrelated, so we can apply a law of large numbers to these quantities. In particular, right, if you pick a sequence of times, tn, that go to 0 fast enough, and then you look at an empirical average of these exponential traces in these TLs, minus their expectation to center them, this converges to 0 almost surely. Okay? And so from that, right, now we can look at the asymptotics of the expectation, and anything in here that'll be of greater order than little o1, we can extract. And so this is now the most recent results that I have to present, which I'm currently in the process of typing up. So for any positive or non-negative R, rather, if you look at this expected trace, here's the explicit asymptotic. So we have a first term that blows up on the order of t to the minus 3/2, which is universal, does not depend on R. But then we have these constant order terms, 1/4 plus R over 2. And with this, right, we can of course now extract the parameter R in the sense that in this empirical mean, right, I can replace this by this term, because anything that is of little order little o1 will get killed in the limit. And then because this is constant, I can just pull it out, and these exponential traces only depend on the eigenvalues. So here is your explicit function that allows you to extract the parameter R from the eigenvalues almost surely. Okay. All right, so I have a bit of time left, so I'll finish things off by going over some future directions that I'd be interested in that are somehow related to this sort of result. So as was discussed throughout the talk, this is a purely asymptotic result, in the sense that what we're looking at is the fluctuations of the eigenvalues, the top eigenvalues in our sample matrices after we've already sent n to infinity. And what we're getting from this is that in principle, we see that these fluctuations, the point process, contains all of the information that we could, about the parameter R, that we can extract almost surely. So what will be interesting to see is if we can somehow extend this to a finite dimensional inference theory. In other words, right, does there exist a sequence of deterministic functions, Fn, such that when you evaluate these in the actual eigenvalues of your sample matrix, allows you to extract the parameter R almost surely in the limit. If we use the results here as an inspiration, then perhaps one idea to do this would be to look at the asymptotics of the exponential trace of the rescaled eigenvalues in your signal matrix with a sequence of tn's that go to 0, based on the intuition that for n very large, these eigenvalues are quite similar to the eigenvalues of the stochastic area operator. However, if we want to try to achieve this using similar types of ideas as we used in this talk, using the Feynman-Katz formula, this poses some serious difficulties. To illustrate this, right, if we look at the Feynman-Katz formula for example, the expectation of these traces in the finite dimensional models, that's what I mean by Fk of the expectation, the Feynman-Katz formula for this is only known to converge to the Feynman-Katz formula for the actual limiting operator in the case of S0, okay? And I'm going to talk about this problem in slightly more details in the open problem session, but essentially what this relies on, proving this sort of convergence of Feynman-Katz formulas, is invariance principles for reflected random walk bridges, which are quite difficult. But in any case, it would be interesting to see if we can somehow extend this understanding to the finite dimensional case. Okay, so this is all I wanted to say about this. So thank you all very much for your attention.
Okay, thank you to the speaker. So we have a lot of time for questions, please. Yes. And with the microphone.
Sorry, is there any link to Maillard calculus here? I mean, because what you are doing is just to consider this the replacement from for the derivative, yeah, in the weak sense stochastically,
right?
Just to use the Ito integral. Is there any link to Maillard calculus that you could do something different to use Maillard derivative?
Perhaps. I mean, I have to admit that I don't know very much about Maillard calculus, so I don't know. But yeah, if this is something, it would certainly be interesting to talk about that and to see if interesting things can be done.
Yes, I was wondering whether one could recover the standard tracy-rhythm results starting from this Feynman-Katz approach. I mean, in the case of beta equals 1, say, or beta equals 2, can you get this Pain-Levé equation somewhere in this?
From the semigroup?
Yeah, I mean, really from the from this Feynman-Katz formula that you have. I mean, this path integral, I would call it, but
that is a good question. I don't think that this has been done, certainly. And one thing that is interesting is that the special structure that you get for beta 1, 2, 4, for example, is very difficult to observe at the level of these operators.
Yeah, that's why I'm asking. Yeah.
It's just a multiplicative factor in front of the Brownian motion, right? So there has been some work done by Gorin and Shkolnikov explaining why beta 2 is special using the semigroup. And basically, the idea is that if you look at these sorts of expected traces, right, there are some very special cancellations that occur between these two terms, this area term and this self-intersection term, when beta is equal to 2. So beta, it multiplies, this is 1/2 beta that you have here. And when beta is equal to 2, you get some sort of miraculous cancellations that sort of explains the special structure. But apart from this, I don't think you can go all the way to recover everything, all the integrable structure that Tracy and Widom derived from this.
So it's in that paper?
Yes, this one. Basically, it's a path transform identity that shows that in that special case, this random variable reduces to a Gaussian, which is somewhat miraculous. And yeah, that's how you can observe that beta 2 is very special.
Okay, interesting.
But even 1, 4, I mean, I don't know that there's any that we understand what makes this special from that point of view.
Yeah, it would be nice to get this out. I mean, yeah,
certainly.
I've been thinking about this for a long time, actually. Okay, thank you.
Okay, Kilian.
So when you expand the expectation into power series in T, can you guess in advance which kind of exponents you will have? So you had a 3/2 and
somewhat. I mean, so what you can do is, you use a Taylor series expansion to expand, this exponential in terms of just powers of the terms inside of here. So you know at the very least that you get, you know, a t to the minus 1/2 coming from this. Now this term, right, when t gets small, it's basically just a straight line from x to x. So here you're integrating minus tx. So you can also guess that, you know, you're going to get the t to the 3/2 by integrating e to the minus tx with this t to the minus 1/2. So there are ways to somehow, you know, infer what that should be. But then you have to deal with this term, which is random, and it's the fluctuations of this one that leads to this, you know, covariance cancellation, and then the expectation of that is where you extract the R.
Okay. And in R, so you will get polynomials, or in the variable R?
What do you mean by you get polynomials?
Because the first one was like a 1-degree polynomial. Yeah,
So here there's no t. That's just a constant order term.
Yeah, but I mean, and the next one in T.
So in the little o one.
Mhm.
Yeah. So here, for example, if you look at powers of these, like the second power of this, and then you start getting, yes, you'll get some various polynomial terms involving R.
Are there further questions? If no, we should thank the speaker.